This is a recorded version of the lecture that I gave in Munich, Germany at the Conference for Physical and Mathematical Ontology. My goal today is to arm you with a new weapon of science, an ancient, forgotten weapon used by the great scientists of old to conquer the physical world. Let's understand a superior version of the scientific method here on Inductica. The problem. Mainstream physics is flawed in both its content and method. Its theories are marked by floating abstractions, quantum non-absolute properties, space and time flowing into one another, and there's very little interest in what these abstractions physically mean. This is the instrumentalist view of science. The idea that it doesn't really matter if we understand what's going on under the surface of physical phenomenon, as long as we have a theory that can recapitulate the observations, that's the best that mankind can ever do. And what this really amounts to is an abandonment of physics. It's a disinterest in what is actually happening in the physical world. And this is an immense tragedy, since science gains its power through an identification of new physical phenomena. As an example, think of the power that we gained by identifying the fact that matter is made of molecules and atoms. Before we had this knowledge, we already knew that chemicals combined in certain ratios. We already knew how to manipulate the world of chemistry on some level, but by understanding the fundamental identity of the entities responsible for these chemical reactions, we gained the ability to customize molecules like never before, opening the doors to thousands upon thousands of new materials that have enhanced our lives in many ways. If modern physicists were in charge of physics back in those days, then chemistry simply never would have identified the atomic theory of matter. Instead, what would have happened is that physicists would have continued to identify deeper and deeper, or really more and more complicated mathematical abstractions, which identified patterns between reaction ratios. And there would be no clear understanding of what these mathematical patterns meant. That is the state of current physics. And this has left us in the community for physical and mathematical ontology with an opportunity. We are the ones who are not content with floating abstractions. We know that these abstractions have real physical meaning. We are the ones with the philosophy required to conquer the ether. So what's our plan? Well, of course, our plan is the scientific method, right? Make a model, have that model make a prediction, then go out into the field and test that prediction. If your model gives a prediction that the mainstream models don't, it validates your theory. I have very bad news, though. This is going to be a very hard road. A road that many great physicists have spent their entire lives on, have died upon, and have made no significant progress. Examples of such physicists are David Bohm, who came up with a rational theory of quantum mechanics, Heinrich Lorentz, who came up with a rational theory of special relativity, and Lajos Janissy, who came up with a rational version of general relativity. All of these men came up with rational versions of the existing theory, but failed to generate any novel predictions. And so they lived and died on this road without making significant progress. Now, let's imagine that you have some kind of novel prediction, that you're able to surpass these giants and you're able to make some prediction that goes against the mainstream. If this happens, you are very unlikely to be funded. The nature of the way we fund physics goes against people who have novel ideas. So you're unlikely to get the money required for such an experiment. Now, even if your prediction ends up happening in the physical world, this actually proves nothing. We are the first to know that a model can be wrong while still making correct predictions about the physical world. In this picture, I've shown the example of the epicycle theory. It was a model where the Earth was at the center, and yet the model was still able to reproduce the correct observational positions of the planets in the night sky by making the planets go in these curlicue patterns. So just because a model makes correct predictions doesn't mean it's right. All of modern physics is a testament to this. But you might tell me, well, James, that's just how science goes. Science is hard. It takes a lot of work. I can't be expected to make progress in just my lifetime. But in the past, science did make progress in a single man's lifetime. And the reason is because there's a better way. Let me show you that better way with a simple example. Let's say that you rub a piece of glass and Then you hold it over some paper and it starts picking up little bits of paper. If you do this, you now know that this tube of glass has a property that other entities don't. You didn't see the property, so how do you know it's there? You saw the action, you didn't see the property. But here's how it works. If you see an action, you can then reason that entities act in accordance with their actions. So an entity that acts in a way that others don't has a property that others don't. So even though you can't see the property, you immediately know that it's there. Now notice that this method I've shown you has nothing to do with guessing and checking. You know it through inference, from observations, and from fundamental principles of how reality works. Now, let's say that you notice that the cork inside of your glass tube also has this strange property. It's able to attract bits of paper. Then you might wonder, well, can this property actually move through objects? So you might set up the following experiment. You might set up a rope, charge up a glass rod, give a rod this electric property you discovered earlier, then touch it to a rope. Once you touch it to the rope, it might make this glass ball have this property. And that would be evidenced by the fact that the glass ball suddenly starts picking up little pieces of paper. Now, you could frame this as a guess and check. You could frame this in terms of the impotent hypothetico-deductive method that is mainstream right now. You could say, hey, I predicted that the ball would get electric, so, maybe the electricity does run through the rope. But simply by reframing it, by refusing to think in terms of the hypothetico-deductive method, you can actually gain certainty about what's going on here. You can instead engage in the following process of reasoning. The tube has the electric property. If I touch it to the rope, then the tube is able to act on the rope. How do I know this? Because of the general principle that entities act at their own location. This is the law of locality. Entities do not act on one another over a distance. They can only act on entities that they are in contact with. The tube was able to act on the rope, and one piece of rope was able to act on the next piece of rope and the next piece of rope until it acted on the ball, making it electric and giving it the ability to attract paper. By framing your experiment in terms of an inference, you now know that the electric property is able to transfer through rope. What I've shown you so far are baby steps. But of course, with enough of these baby steps, each step gaining certainty about some small part of the physical world, this eventually reaches a critical mass that gives us immense power over nature. What I've shown you today, the fact that electricity can run through objects, is the core of our power grid, allowing us to transfer energy wherever we'd like with relative ease. What I've shown you here is the method of inference. It grants explicit knowledge of the nature of physical processes. Notice that we're not guessing and checking and saying, oh, well, the physical process I had in mind made correct predictions, so I guess maybe it's true. No. Through inference, you know immediately that the physical process you had in mind is what is indeed going on. If you frame the inference properly, you can do this. And when you think about it, is it any wonder that the hypothetico-deductive method has led to a set of mainstream physicists who have a disinterest in underlying physical facts? If you can never really prove what's going on underneath the surface of your observations, then what's the point of understanding actual physical facts? I mean, the only point is just if you can make predictions or not. So we can see that the vices of modern physics are in large part caused by the hypothetico-deductive method. Now notice that the method of inference also achieves a much higher level of confidence. We are reasoning from observations, which can be known with certainty, and we are reasoning from prior premises, which themselves have been proven through observation. And as long as we use proper deduction, we can gain a very high level of confidence in our understanding of the world that comes from this method. And of course, the method goes through first observations, deductions from those observations, and that results in knowledge that goes beyond the reach of the senses. Now, when you accumulate enough of these baby steps, they start to build upon one another, not only so that applications become possible, but these baby steps culminate in great discoveries. What you see on the screen right now is an experiment done by James Prescott Joule. What he did is he showed that heat is the motion of molecules. How did he do this? It was through inference, not through the hypothetico-deductive method. He took a weight, he let that weight fall. He knew that the amount of work that was exerted by that weight was equal to mgh. He knew that that same amount of work would be transferred via a cable into a paddle, and that the motion of that paddle would then move into the motion of the molecules inside of the water. He knew that however much work the weight did, that was the same amount of work that was put into the water molecules, the same amount of motion put into the water. Once the water stopped swirling, Joule measured the temperature of the water and found that the temperature always rose in proportion to the amount of work put into the system. By doing this, James Joule was able to prove that heat was the motion of molecules, or at least that it was related to the motion of molecules. Now, once again, notice that he did not use the hypothetico-deductive method. He did not simply say, my prediction came true. I guess maybe I might be right. No, instead what he was able to do was this. He said, I know that there are molecules in the water. I know that the molecules are getting a certain amount of work put on them. I know the molecules will then move at a certain rate. He then showed that the amount of movement that they gave is proportional to the temperature, establishing with certainty that there's a link between heat and the motion of molecules. Now, this method that I'm showing you today is not just something that happened to work in the past. Maybe you might be thinking, okay, you've given me a lot of examples from the past, but maybe we've just come too far. We can't use this method anymore. That's not the case. We can use this now to make powerful inferences about the physical world, and I will show you one that I can do for you right now. I will prove the existence of an electromagnetic ether. After this inference, you will see that the ether will be known for sure, with certainty, not just a likely hypothesis that happens to tie a lot of different observations together. In order to do this, I will start by showing you the electromagnetic wave equation. By dissecting the physical meaning of this equation, we're going to learn something about the entities that lie behind it. So let's say we have an electromagnetic wave, and we have at each location different amounts of electric field at different locations. And let's zoom into these three locations. You see these three dots on the bottom. These are three locations that we are going to be thinking about. To understand the wave equation, we're going to have to understand that second space derivative, that derivative on the right. We need to understand what the second space derivative means. Okay, why is that? Because the second space derivative will relate to the second time derivative of the electric field. So in other words, the electric field in any given location changes in proportion to the second spatial derivative at that location. Okay, so what's the physical meaning of the second spatial derivative? Well, to understand that, let's first understand the meaning of the first spatial derivative. What I've shown here in the bottom diagram is that the first spatial derivative shows us how much the electric field changes as we move from this central location to either the left or the right. You can see on the right, there's a small increase, and on the left, there's a larger decrease in this particular example. So now, what does the second derivative physically represent? Well, if we look at this equation, we can see that the second derivative is the difference in the difference. Takes a derivative of the first derivative. It's the right minus the left, the change on the right minus the change in the left. Let's understand what that means in greater detail. I'm going to analyze an example. Let's say that on the right, the electric field's a little higher, and on the left, the electric field's also a little higher. If this is the case, then we can see that the first derivative on the right is positive. You can see that I made it positive in the diagram here. Now, the first derivative going to the left is negative. And the reason it's negative, you can see based on the signs that I've added in this equation, it's because we're taking one step backwards. The delta x is negative. So what does this lead to? If you look carefully, you'll see that this second derivative, this second spatial derivative, is a positive number in this case. Now, if the second spatial derivative is a positive number, that leads to a positive second time derivative. So what does that mean? Well, it means that if the neighboring locations have more electric field in them, then that means the central location will increase in its amount of electric field over time. Let's look at another example. In this example, the two neighboring locations have less electric field. You can see from the equation, based on the signs that I've added, and you can pause the video, you'll see in this example, the second spatial derivative is negative. And as a result, the second time derivative will be negative. The amount of electric field over time will decrease. So what's going on? What we have here is any one location increases if its neighbor has more, and it decreases if its neighbors have less. It's as though the electric field is flowing from one location to another. It's disappearing from the locations with more electric field and moving into the locations with less electric field. So let me show you one more example here. You see on the left we have a very large positive difference, and on the right we have a small negative difference. Now you can see, based on the signs that I've added in the second derivative equation, that the first term is negative and we're subtracting a negative term. However, the negative term on the left that we're subtracting is a larger number. And as a result, this whole thing is going to end up positive. You can pause the video and check the signs. This whole thing will be positive because the change on the left is greater than the change on the right. Now, if this whole thing is positive, then what does that lead to? It means the electric field at this position will be positive. It's as if electric field is flowing into the center from the left, but flowing out of the center to the right, but then the flow from left to the center is greater than the flow from the center to the right. And as a result, there is an increase at the center. Now, what I have just shown you demonstrates that there is an entity at each of these locations. And if there's an entity, it means there's an ether, because it means that there's an entity at all of these locations where there's an electric field. And if there's an entity at each location where there's an electric field, that's an ether. It's an entity at each location. Now, how do we know it's an entity? It's because it has both of the characteristics of an entity. First, each of these locations has a capacity for action. What is that? That's the electric field itself. The electric field tells us what kind of action could happen at a given location. So there's something there that can act. Further, there is something there that can be acted upon. This is the second characteristic of an entity. How do we know there's something there that can be acted upon? Well, because any one location changes in its electric field in accordance with the electric fields at neighboring locations. These neighboring locations are therefore acting on this location. Therefore, there's something at this location that can be acted upon. Therefore, this is an entity. At every one of these locations is an entity. I've now proven the electromagnetic ether. My proof requires that we accept my concept of an entity, so I'm going to give some argumentation for that. Again, my two aspects of an entity is it has to act at a certain location and it has to have the ability to be acted upon. Now, before I go any further, I need to emphasize that I'm not saying that this entity, whatever it is some kind of substance or material. You know, it's not made of carbon or anything like that. It's probably not made of any material that we've ever come across so far. All I'm saying is that it is an actor and a reactor. It's an entity. There's a reason I'm using such a generic term. Now, we know this is an entity because this standard, these two criterion, are the standards you've been using your entire life to determine if something is an entity. So for example, you know that a person is an entity because they act in certain ways. They reflect light, they emit sounds, they move around, and they can be acted upon. If you throw a tomato at someone, they will change. Why? Because the tomato acted upon them and maybe made them very angry. This is also the standard on which you would identify something as not being an entity. So for example, if you see a TV character, then the TV character acts, but you'll notice that you can't act on the TV character. If you throw a tomato at the screen, the tomato will act on the screen, but it won't act on the character. The character will continue acting as he did before. If you threw a tomato at someone and the tomato simply passed through them, then you would entertain the idea that you're actually dealing with a hologram or a hallucination, not a person, not an entity. Why is this? Because the thing acts, but it lacks that second capacity of being able to act upon it. So this is the standard you've been using your entire life, and the standard that you use in science when you decide that something is an entity. To deny that these objects are entities, you'd have to deny that other things are entities, that salt shakers are entities, that the food you're putting in your mouth is an entity. Because the standard on which you identify something as an entity is that it acts at a certain location and it can be acted upon. Now notice that I'm arguing from fundamental principles here. I'm not arguing from common sense. Now, what I'm saying might comport with common sense. But what's important is that this is the proper conceptualization of an entity, that this is the right way to split the world up into things that can act and to be acted upon. How do we know that's proper? Well, because it's important to tell the difference between things that can act and be acted upon and things that can't. There's an important difference between a person and a hologram. So you can see that with these broad principles and their application to the electromagnetic wave equation, we've proven the existence of an electromagnetic ether. Next, I'm going to use this exact same argument to prove the existence of a gravitational ether. Now, when you write out the gravitational wave equation, you get this equation. Now, this is an equation with many components, h, but if you look at this equation, you will see the same pattern that we saw in the last equation. We see the second time derivative of all of the different components of h relies on the second spatial derivative. Now, this ends up being a 3D spatial derivative, but it's still a second spatial derivative at neighboring locations. So each of these h's is a different property of each location, and each of those locations changes in that property based on the value of h's at neighboring locations. Therefore, there is a gravitational ether. Now, you might be wondering, why am I calling this a gravitational ether? Like, you already proved the electromagnetic ether. Shouldn't you just call it the ether? Why are you differentiating? The reason is because at this point, I haven't proven that these are all the same ether yet. These are different things that, so far, based on what I've shown you, exhibit different properties. They have different properties and they act on one another in different ways. So there's no proof they're the same thing. Remember, inference is not the application of common sense. It is the rigorous application of carefully derived earlier principles using exacting logic. I'm going to use this same argument now to prove the existence of a matter ether. If you look at the Schrödinger equation, an equation which identifies a wave that's associated with matter, you will see that the same reasoning applies. It's a little different in this case because we can see that it is the first time derivative of the property that changes in accordance with the second spatial derivative of that property at neighboring locations. And what is this property again? Like, how do you know this is a property? Well, remember, psi relates to the probability of a detection event. How does that relate to the actual properties of the ether? I don't know, but we know that psi means something physically. It's somehow related to a physical thing because it accurately predicts the probability of detection events. So as a result, we know it has something to do with some property at that location. And each of these properties change over time in accordance with the distribution of the property nearby. And so there are matter entities. There is a matter ether that acts on each bit of other matter ether at neighboring locations. Now, you might have noticed that there's a little hiccup here. The Schrödinger equation is a complex differential equation, and its solution is generally complex. It has a real and imaginary part. But I have to thank Travis Norson here. His book shows that this is just an artifact of the way we think about the Schrödinger equation. You could easily write the Schrödinger equation as a real part F and an imaginary part G. Then you can simply reframe the Schrödinger equation as two coupled equations that are both completely real. So the imaginary aspect of psi is just a mathematical convenience. It is not some indication of complex metaphysical properties of what's going on here. It's just convenience. Now, there's another argument that needs to be addressed here, and that is the fact that the quantum mechanical wave equation is not in general a function of three-dimensional space. It's actually a function of 3n dimensions. Okay, what the heck does that mean? Well, 3n plus 1 if you count time. And the reason for this is the Schrödinger equation can actually keep track of many particles all at the same time, and it needs to in the case of entangled states. And when you keep track of the wave equation for entangled states, you actually need to use one of these 3n dimensional functions. So that kind of calls into question the idea that the Schrödinger equation solution actually means anything physical. This argument can actually be overcome if we dive into the nature of configuration spaces, but I'm not going to do that in this video. What I will do in this video, though, is note that my argument still holds for the case of a single particle. If there is just the presence of a single particle, say like in the double slit experiment, then all of my reasoning still holds. This Schrodinger equation holds straightforwardly, and my argument applies straightforwardly. And what this indicates is that in the case of entanglement, there might be more going on that's interesting that we should study later. But all of that extra stuff, as interesting as it may be, is simply extra stuff that acts on top of the fact that there is a medium here, and perturbations of this medium constitute an aspect of matter. Now that I have proven the existence of a matter medium, I will now prove the existence of one final medium. I will call it the duration-altering ether. Now, in order to understand this example I'm about to give you, you need to set special relativity aside. First of all, it's a flawed theory. Second of all, you just don't need it to understand the argument I'm about to make. And if you start applying it, it's going to be really easy to get confused. So just set all of that aside. You don't need to abandon it. You just have to set it aside and look at the observation I'm pointing to here. So the observation is going to be a certain thought experiment. Let's say you got a red ship moving to the right at a certain constant speed. You have a blue ship moving to the left at a certain constant speed. And you have a space station here in green that is stationary in our frame of reference. And let's say that aboard each of these ships, you build an atomic clock. And let's say, for the sake of argument, that you build an atomic clock by first creating a radioactive isotope in a particle accelerator. You then attach that radioactive isotope to all the needed circuitry to build an atomic clock. You then let the ships begin floating in the direction of their velocity. Okay, now at this point, the red ship and the green space station will be right next to each other. And let's say that at this stage, the red ship and the green station synchronize their clocks. Okay, so their clocks are now at the same starting point. You then let them progress, and then let us say that the red and the blue ships synchronize their clocks. You then allow the blue ship to progress until it meets up with the green space station, and then let us compare the blue clock and the green clock. If you do this, you will find that less time elapsed on the blue clock than elapsed on the green clock. Now, in other words, the green isotope, and I want you to focus on this. Don't focus on the clock, focus on the isotopes. The green isotopes changed more than the red and blue isotopes. If you conduct this experiment, this is what you will see. What can be inferred from this experiment? Okay, follow me on this. The green isotope changed more than the red and blue isotopes. What could have been the cause of this difference in the rate of change? Well, there's only one thing that was different here, and that's the state of motion of the three objects. Now, note, of course, we could have chosen a different reference frame. We could have chosen to make the blue ship stationary, but however you want to frame it, there's a difference in speed here. The only thing that could have caused the difference in the rate of change of these isotopes is the difference in velocity of these three objects. And that difference in velocity is there no matter how you want to frame it. Okay, now, a difference in velocity is always a difference with respect to something. What could that something be? Well, whatever it is, it's a something that has to be at the location of the ship. How do we know that? The reason we know that is because whatever this something is, motion with respect to it is causing the difference in the rate of change. That means that something is acting on the isotope, causing it to change more slowly or more quickly. Something acting on the isotope has to be at the location of the isotope. That's the principle of locality. As a result, we know that anywhere where you can conduct this experiment, there exists an entity at each of these locations. There exists a medium, and your motion through that medium determines the rate at which these processes of change transpire. I have thus proven the existence of an ether that causes duration dilation. And I have to give some credit here to Daniel Harris. You can see a link to his YouTube channel in the description. He showed this thought experiment, and this is very similar to one of his thought experiments, so I have to give him credit for that. And of course, a similar argument to this can also be made for length contraction. Now, with a further inference, a very simple inference, we can connect the ethers. First of all, the matter and electromagnetic ether are related or the same ether. How do we know this? Well, because of electromagnetic forces. This shows that the ether is able to act on charges, and charges are matter waves, or at least they're somehow related to the matter waves. So this shows that the electromagnetic ether acts on the matter ether. Further, The matter ether acts on the electromagnetic ether. How do we know that? Well, because some matter is charged, and so it affects the electromagnetic ether. Further, we need to think about particle creation and annihilation actions. So, for example, when a positron and an electron collide, they turn into a photon. So this is one more example of the matter and electromagnetic ethers either acting on each other or just being the very same ether. Now, I suspect that if we look at some of the interactions that happen in particle colliders, we're going to be able to infer a lot more about the nature of the ether. So I think with the proper kind of work and the proper kind of reframing, we're going to be able to rehabilitate much of the data that has been gathered in particle physics and reinterpret it to make much more powerful conclusions about the nature of the ether. Let's make some further connections. The matter / electromagnetic ether is related to the gravitational ether, or it's the very same ether. How do we know this? It's because gravitation bends light and matter waves. So, the Earth, of course, moves differently as a result of the sun's pull. So that's the gravitational ether acting on the matter ether. And of course, light is changed in its path by the gravitational ether. So the gravitational ether also acts on the electromagnetic ether. Now further, matter waves cause gravitation, so matter waves act on the gravitational ether. And light waves probably cause gravitation, so the electromagnetic ether probably acts on the gravitational ether directly. We actually haven't proven that directly through experiment yet, but it's probably the case. So what conclusions can we make? Well, first of all, there's an electromagnetic ether. I showed that with the electromagnetic wave equation and a dissection of the physical meaning of that mathematics. Second, there's a gravitational ether. I showed that through almost the exact same argument applied to the gravitational wave equation. Further, there is a matter ether. I showed that through the same argument applied to the Schrödinger equation. And finally, there is a duration dilating ether. There is an ether that when you move with respect to it, this changes the duration of certain physical processes. And finally, I have shown that all of these ethers are connected to one another. So what this does is it fully justifies the approach of certain thinkers like Dialect or Chantal Roth. What Chantal is doing, and you can see her video in the description, and I interviewed her. What Chantal is doing is she's creating mathematical models that model the ether and show what kind of medium could be responsible for all of these different interactions that are happening with one another. She is trying to find an integrated view of the ether. Now, thanks to my argument today, we can see that this isn't just a good idea because it happens to connect a lot of dots. It's right on some level. We know with certainty that it's the right kind of thing to do. We know that there's an ether. We know that all of these different aspects of the ether are connected to one another. It's just a matter now of figuring out the nature of the ether. This method of inference is going to make possible further inferences. Let me show some of them to you. So first of all, we should apply this same kind of reasoning to the Dirac and Klein-Gordon equations. The reason for this is that they are the relativistic versions of the Schrödinger equation, and we might learn more about that by moving into that context, making deductions in that context. And if you look at this equation, you can already see that it has a similar form that we're going to be able to use the same basic reasoning on. Another thing that should be on the top of our priority list is a deduction of duration and length changes to the hydrogen wave function. That is the wave function that represents the electron cloud around the hydrogen atom. What I'm talking about specifically here is trying to deduce what happens to the shape of an electron cloud when that electron cloud is moving through the ether. When the electron cloud moves through the ether, that's going to change the nature of the central potential, and it's also going to change the speed of the wave as it goes in each direction. Now, I suspect that when you apply these changes to the nature of the Schrödinger equation and the nature of the wave function, you're going to get length contraction. You're going to get a deduction of length contraction from this fundamental nature of matter. You're also going to get duration dilation in the form of a changing frequency for this wave, so it'll change at a different rate. And I think what's also going to happen is that the emission lines are going to be different for hydrogen. You're going to find different spacings between the hydrogen energy levels, and I think that those changes are going to be in line with the perpendicular Doppler effect. And so I think all of that can be explained by deductions from the nature of this wave and from our new understanding that this wave is, with certainty, a wave of the ether. Now, Dialect on his channel has already done this to some extent, so we should continue the work that he explained in that video. He explained some of the work of Valerie Lindner, and in that work, Dialect shows us how the fields change, specifically how the vector potential and the scalar potential change in a moving frame. And he gives a plausible argument for how that's going to lead to a length contraction, a shrinking of matter, but it's not a completely rigorous argument. And I think that by making arguments from the Schrödinger equation, from the equation that really represents something about the nature of matter, we can make this completely rigorous. We can show the particular mechanism by which motion through the ether causes length contraction and duration dilation. What we also might be able to do is make some kind of deduction about changes to the inner nature of the wave function that might identify the inner mechanics of the gravitational force. That's a little speculative, but worth looking into. Now, as you go forward, I highly recommend that you start changing your mindset if you want to discover new things about the ether for yourself. What is that going to entail? First, what I'll say is that I'm not against the hypothetico-deductive method. I'm not saying don't do it. I'm just saying it's weak. It's not as effective as the kind of method I've presented today. And what you're going to have to do is to retrain yourself to search for inferences instead of thinking about ways to devise confirming experiments or predictions that go against the existing theories. You're going to need to think about ways to reframe your research. If you have a hypothesis, start thinking about ways that you might make some new observation. And that new observation is not to make a different prediction. The purpose of that new observation would be to give you that little bit of information that's necessary to finish an inference. Now, by the way, you're already doing this. You're already making inferences all the time. It's not like people don't use this method. I'm just saying that you should start using it as a matter of principle. You should use it with the same kind of regularity and careful thought that you have applied to the hypothetico-deductive method. I've painted a pretty dismal picture of what the hypothetico-deductive method looks like in practice. You guess, you check, and then even if everything works out perfectly, you still have an uncertain conclusion. So what is the path that lies before us if we choose the path of inference? Well, if we choose the path of inference, we first have to get clear on what observations and reasoning steps have been proven so far. That's really key. You can only reason from things that have been fully proven. In this video, I've reasoned from the Schrödinger equation on the premise that, well, at least it gives correct predictions about something that's happening at each location, so we can be certain that the wave function gives some kind of property there. You have to be really careful about what you use in an inference. So you have to check with great clarity what these theories mean you're making deductions from, and if you're sure that they are actually correct theories, or at least if you're deducing from the parts of them that have been fully proven from observation. Now, the next step is that you're going to make inferences that prove new aspects of nature. If you get clear enough on the prior context of knowledge and you think long and hard enough about it, you will find some new ways to dig into nature a little bit further. And these baby steps, each of them is going to make possible larger and larger steps. Our end goal should be the discovery of new phenomena and new technology. This is how we're going to show the mainstream that we have a better approach. It's not going to be by coming up with one more hypothesis that happens to agree with all of the mainstream predictions. So what are our next steps? What should you do today to start applying the method of inference to your own investigations? First, as I said, you have to get clear on what you know for certain and what's just a hypothesis. You then have to take your hypotheses or your models, if you've made mathematical or computer models of the nature of the ether, you have to take these models and reduce them down to what is provable. A lot of these models are mechanical analogies. For example, Chantal is working on an analogy of the ether to an elastic solid. It's really important to note that such a model is only an analogy. The ether probably isn't literally an elastic solid. Its parts relate to each other in a way that is analogous to an elastic solid. Which parts of these are analogy and which parts are real relationships? We need to strip our hypotheses to just the quantities, the properties, and the relationships between those properties that we know for certain. Only then can we start making inferences from that knowledge to identify further facts about the nature of the ether. And of course, something else that needs to be done is you need to devise new observations, new experiments that are tuned to give you that last bit of information that you need in order to complete your inference. Or in many cases, that won't be necessary. There's a lot of data out there. Maybe all that is required for you to do is to look up the data in some experiment that has already been done, and that will give you the information required to complete your inference and discover something new. And once all of these inferences reach some critical mass, that will make possible some new application. And I see this as the ultimate justification of the method of inference and the ultimate justification of approaching physics from a perspective of being interested in actual physical relationships, not just mathematical abstractions. That is how we're going to convince the world that this approach is superior. And on a final note, I think history has given us an opportunity to show the world what's possible. This isn't just about physics. You see, people once looked to Newton's method and his mechanical universe for guidance. They looked to his method as being the perfect example of logic in action, of looking at reality and knowing it. And they looked to his view of the universe, a universe of knowable mechanical objects acting on one another. They looked to that as a model for what the universe fundamentally is, a logical place that has rules that are manipulatable by man so that we can take advantage of them. But I don't think this is the case any longer. Because mainstream physics projects a world of floating abstractions and of non-absolutes, people can't use it as a role model anymore. And if this is the case, is it any wonder why politics is irrational? After all, why be rational if physics isn't even rational? Why be rational in human discourse if the core of physical reality, the thing that everything is based on, if that isn't even rational? Why be truthful when quantum mechanics teaches us that there's no objective truth to be loyal to? So I think this has given us an opportunity. If we can show the world that these theories actually mean something in reality and that they should be replaced with more rational theories, we can show the world that we do not live in a quantum irrational flux, but rather we can show them that we live in a rational, logical world that is ours to know and to explore. Thank you.